So this video is for those of you who want to get an introduction into electronics. So one of the first components that we're going to talk about is resistors, because typically you'll find them in almost every electronic circuit. Resistors are designed to limit the amount of current flowing in the circuit. And you could calculate the amount of current flowing in a circuit using Ohm's law. V equals IR. V stands for voltage, measured in volts. I represents the current measured in amps. R is the resistance measured in ohms. The current flowing through a resistor is the voltage across the resistor divided by the resistance itself. So let's say we have a battery attached to a resistor. The long side is the positive terminal of the battery. The short side is the negative terminal of the battery. And let's use a 12-volt battery. Conventional current is going to flow from the positive terminal of the battery through the resistor back to the negative terminal of the battery. Conventional current flows from a high potential to a low potential, but in actuality, electrons flow in the other direction, from the negative terminal to the positive terminal. So that's really what's happening in this circuit. Electrons are the charge carriers. They're the ones that are moving through the metallic conductor. But now let's make a table that shows the relationship between resistance and current. So let's say the resistance is 3 ohms. Using this formula, if we take 12 volts divided by 3 ohms, we're going to get a current of 4 amps. Now, what if we increase the resistance? Let's say from 3 ohms to 6 ohms. What's going to be the current? Well, using the same formula, if we divide 12 volts by 6 ohms, we're going to get 2 amps. And so note the relationship between resistance and current. If we increase the resistance in a circuit, the current decreases. And so we could use this device to control the amount of current that is flowing in a circuit. If you want to increase the current, you can decrease the resistance. If you wish to decrease the current, increase the resistance. Now sometimes you may need to decide what resistor to use in a circuit. And one important consideration that you need to take into account is the power rating of a resistor. So let's say we have a battery attached to a resistor. And let's say this is a 100 ohm resistor and the power rating is 1/2 watts. Power is equal to voltage times current. It's also equal to the square of the current times the resistance, and it's equal to V squared over R. So you could use any one of those 3 formulas to calculate power. Now, this is important because if you apply too much power to a resistor or too much voltage, the resistor can burn up. It can get hot, and that could create a lot of problems. So you need to control how much power you deliver to a resistor, because it can only dissipate so much without damaging itself and other nearby components. So what we're going to do in this example is, given the resistance and the power rating of the resistor, what is the maximum voltage that we should apply across this resistor? So we're going to use this formula. P is equal to V squared over R. Now, because we're solving for V, we're going to rearrange the equation. I'm going to multiply both sides by R. So I get V squared is equal to the power times the resistor. Taking the square root of both sides, we get the formula to calculate the maximum voltage that should be applied across the resistor. So V is equal to the square root of P times R. So here we have a 1/2 watt resistor, and the resistance is 100 ohms. So half of 100 is 49. And the square root, it's 50. Whoa, half of 100 is not 49, it's 50. But you know what? It is easy to take the square root of 49. That's 7. So if you want to get a ballpark of your answer, you know it's close to 7. The square root of 50 is about 7.07 volts. So that is the maximum voltage that should be applied across this resistor if you don't want it to overheat. Now the next thing that we need to talk about is how you can connect multiple resistors together. If you wish to increase the resistance in a circuit, you want to add resistors in series, because the total resistance of resistors connected in series is the sum of each individual resistor. So the more resistors that you add, the greater the total resistance will be. In a parallel circuit, the more resistors you add in parallel to each other, the total resistance actually goes down. To calculate the total resistance, you can use this formula. It's 1 over R1 plus 1 over R2 plus 1 over R3 raised to the minus 1. And I'm going to give you an example of that shortly. But right now, I want you to understand something. In a series circuit, there's only one path for the current to flow. And this is the only path that it can flow from A to B. In a parallel circuit, there's multiple paths for the current to flow. Going from A to B, the current can flow through R1, it can flow through R2, and it can flow through R3. And so that can help you to distinguish whether if two components are connected in series or in parallel. If there's only one path for the current to flow, it's connected in series. If there are multiple paths for the current to flow, it's connected in parallel. Now there's some other important things to take into account here, because in a series circuit, the current flowing through each resistor is the same. So the current flowing through R1 is called I1. The current flowing through R2 is I2. Each of these currents, they're the same current. I1 is equal to I2, and that's equal to I3. Now, in a parallel circuit, the voltage across each resistor is the same. So the voltage across R1 is V1. The voltage across R2 is V2, because they're connected across the same 2 points. So that's another thing you need to be aware of when dealing with series circuits and parallel circuits. In a series circuit, the current flowing through each resistor is the same. In a parallel circuit, the voltage across each resistor is the same. Now, let's say we have two 10 ohm resistors. There's a lot of things we can do with that. With those two 10 ohm resistors, we can get 3 different resistor values. We could use one of the 2 resistors to get a resistance value of 10 ohms, or if we wish to increase the resistance, we can connect the 2 resistors in series. And so the total resistance across these 2 points, let's call it point A and B, is now R1 plus R2, so we get 20. Now, if we wish to decrease the resistance, we can connect the 2 resistors in parallel. Now, whenever you connect 2 resistors in parallel, if the 2 resistors have the same value, if they're identical, the total resistance of the 2 identical resistors will be half of their respective values. So it's going to be 5 ohms. So thus, if you want to increase the resistance, connect resistors in series. If you wish to decrease the resistance, connect them in parallel. Now for those of you who want to see the calculation, it's going to be 1 over R1. R1 is 10 plus 1 over R2 raised to the minus 1. So 1 over 10 plus 1 over 10 is 2 over 10. And when you raise something to the minus 1 power, you basically need to flip the fraction. If you flip the fraction, the exponent will change sign. It will change from being negative 1 to positive 1. 10 over 2 to the first power is simply 10 over 2. And 10 divided by 2 is 5. And so anytime you connect 2 identical resistors in parallel, the total resistance will be half of their respective values. Now the next type of device that we need to talk about is the light bulb. The light bulb converts electricity into light energy. And this particular light bulb does so through a process known as incandescence. In incandescence, what happens is when a metal gets very hot, it's going to become red hot first, and as it gets hotter, the color changes. It'll turn yellow, it may even be white hot. And so when a metal is very hot, it begins to emit not only heat energy, but light energy. And so incandescence is a process where you can generate light by heating up a material. In this light bulb, there is a tiny wire called a filament. So this is going to be green color. And the reason why it has to be so thin is because if you have a lot of electrons flowing through a very thin wire, it's going to be very easy to heat up that metal wire. And as the metal wire gets hot, it's going to emit light if it reaches a high enough temperature. And so that's incandescence. When you apply an electric current through a very tiny piece of metal, it can get hot to the point where it emits light. Now, with these types of light bulbs, they're not very efficient in generating light energy. They work, but a lot of the energy is wasted as heat energy. They generate a lot of heat. And there's another type of device that we could use that can also generate light energy. And this is known as an LED, a light emitting diode. Let's use a green LED. A light emitting diode also converts electricity to light energy, but it does so more efficiently. It doesn't use the process of incandescence. In fact, LEDs are monochromatic light sources. They generate light of one specific wavelength. And as a result, these devices are very efficient at converting electricity into light energy. Very little heat is generated. They don't use up that much current. A typical green LED has a voltage drop of 2 volts. And the amount of current that usually flows through an LED can vary between 0.1 milliamps to 20. If you put too much current in an LED, it can burn out. So there are limits. When you're buying an LED, you need to look at the manufacturer specifications in terms of what the maximum forward current should be. But this is typically the range of most LEDs that you'll encounter in electronics. Now let's say we have a 9-volt battery. And we want to determine the value of the current limiting resistor that we should use in order to get a current of 10 milliamps flowing through this LED. Because you don't want too much current to flow in it. So this is when it's useful to add a current limiting resistor. How can we determine the resistance value that we need? Well, for one thing, we need to determine the voltage across the resistor. The LED will use up 2 volts out of the 9 volts that the battery is providing to the circuit. So the resistor is going to take up the other 7 volts. And this is the basic idea behind Kirchhoff's voltage law. The sum of the voltage drops in a closed loop or in a closed circuit must add up to 0. The battery has, because it increases the energy to a circuit, we're going to put a positive voltage to it. The resistor and the LED, they absorb energy from the circuit, so we're going to put a negative value. If you add 9, -7, and -2, you'll get 0, which satisfies Kirchhoff's voltage law. Now, in order to calculate the resistance that we need, we could use Ohm's law. V is equal to IR. So solving for R, it's going to be the voltage divided by the current. So we have 7 volts across the resistor, and we want a current of 10 milliamps across it. By the way, if you divide volts by amps, you're going to get the resistance in ohms. If you divide volts by milliamps, you'll get the resistance in kilo ohms. So just be aware of that. So if we take 7 volts divided by 10 milliamps, this is going to give us 0.7 kilo ohms. Now 1 kilo ohm is 1,000 ohms. So 0.7 kilo ohms is 700 ohms. So we need a 700 ohm resistor in order to get a current of approximately 10 milliamps in a circuit. Now the next type of device that I want to talk about is something known as a potentiometer. Now you might be wondering, what is a potentiometer? A potentiometer is a variable resistor. It's a device where you can adjust the resistance of a circuit. And that's pretty useful because you could use that to control the voltage across an element, or you could use it to control the amount of current in a circuit. But let's talk about the potentiometer. So here is the electrical symbol of a potentiometer. You can draw it this way. You can draw it this way. It's a variable resistor. But let's use this version of it. I want you to understand how it works. So let's call this point A, point B, and point C. Now let's say this is a 100 kilo ohm potentiometer. If C is at the middle of A and B, the resistance between A and C will be 50K. The resistance between B and C will be 50K. But the resistance between A and B is always 100K, and that's important. So let's say we move up point C closer to A. And this is still a 100K resistor. So the 100K potentiometer will still have a resistance of 100 kilo ohms between point A and B. That's not going to change. What changes is the relative resistance between A and C and B and C. So now, if the resistance between A and C is 25K, the resistance between B and C will be 75 kilo ohms. The sum total will always be 100 kilo ohms. And so sometimes you don't need to use all 3 points of a potentiometer. You may only need to use 2 of the 3 points. And so if we only use A and C, we can adjust the resistance of A and C from 0 kilo ohms to 100 kilo ohms. Now there's many applications of potentiometers. We won't be able to cover all of them in this video, but let's talk about the basics of it. One useful application of the potentiometer is using it for brightness control. Let me draw a better circuit. Sometimes my drawing skills is not what it should be. So in this example, I'm only going to use 2 of the 3 parts of the potentiometer. So let's use a 9-volt battery. And we're going to use a green LED with a voltage drop of 2 volts. Let's call this R1 and R2. And let's say that R1 is a 10 kilo ohm potentiometer. Let's call this point A, B, and C. So between A and B, the resistance is always 10 kilo ohms. But between A and C, it can vary between 0 and 10 kilo ohms. Now, if R1 goes to 0 kilo ohms, that's dangerous for the LED, because without R2 there, we could have too much current flowing through the LED. So R2 it serves to protect the LED in the event that R1 is tuned to 0 kilo ohms. So the maximum current of a typical LED is 20 milliamps. To determine our R2 value, let's assume R1 goes to 0. So R2 is going to be the voltage, which if we take the difference between 9 and 2 volts, the maximum voltage across R2 will be 7 volts, divided by a maximum current of 20 milliamps. Now, if you want to convert from milliamps to amps, divide by 1,000. 1 amp is 1,000 milliamps. So 20 divided by 1,000, that's 0.02. So 20 milliamps is 0.02 amps. 7 divided by 0.02 is 350. So we want R2 to be 350 ohms. So if R1 is set to 0K, the most or the maximum amount of current that we're going to get in the circuit is 20 milliamps, which means the LED will be super bright. But now, if R1 is tuned all the way to 10K, then the total resistance in the circuit will be 10K plus 350 ohms. So thus it will be 10.35 kilo ohms. Keep in mind, 350 ohms is 0.35 kilo ohms. So the max current, which will be voltage divided by resistance, that's going to be, we're going to have 7 volts across these two resistors equivalently if this goes up to 10K. So the total voltage across the two resistors will be no more than 7 volts due to the 2-volt drop of the LED. And the total resistance is 10.35 kilo ohms. Now remember, if you divide volts by amps, you get the resistance in ohms. If you divide volts by kilo ohms, you're going to get the current in milliamps. 7 divided by 10.35 kilo ohms is going to give us a current of 0.676 milliamps. So with this potentiometer, the current in the circuit can vary between 0.68 milliamps and 20 milliamps. So when R1 is set to 0K, the current is going to be very high, which means the LED will be super bright. If we adjust R1 to 10K, the current flowing in the circuit will be very low, which means the LED will be very dim. So thus we could use a potentiometer for brightness control. The potentiometer can help us to adjust the resistance in the circuit, thereby adjusting the current flowing in the circuit, thus controlling the brightness of the LED. So that's one of the many applications of potentiometers in electronics. Now, before moving on to the next topic, I want to mention a few things. For those of you who want more information on potentiometers, LEDs, how to calculate the current in series and parallel circuits, and even other things that I'm going to talk about later in this video, I'm going to post some links in the description section below this video. So feel free to take a look at that if you want access to other videos regarding electronic circuits. In addition, I have a playlist on electronics that you could find at my website, www.video-tutor.net. So if you want to see a playlist with electronics topics, feel free to take a look at that. And for those of you who want to see what equipment I've used when building electronic circuits and other science and tech stuff, you can check out my Amazon store. It's amazon.com/shop/the organic chemistry tutor. So if you want to see what type of multimeter I've been using or what type of electronic components that I've experimented with, and if you want to test it out yourself, you could find it all at this link. So feel free to take a look at that when you get a chance. Now the next thing that we're going to talk about is the voltage divider network used in resistors, because the potentiometer is very useful in this case. So let's say we have two resistors and both of them is 10 ohms. And let's say we have a 12-volt battery. The voltage across the 10 ohm resistor will be half of the 12-volt battery. And let me give you the formula associated with this type of circuit. Let's call this R1 and R2. And let's call the voltage of the battery V. And we're going to say the voltage across R2 is the output voltage. The output voltage is going to equal the input voltage times R2 divided by R1 plus R2. Now let's adjust this circuit. Now this circuit works by reducing the voltage through power dissipation. The energy provided by the battery, some of it is dissipated in the form of heat. And because we're losing energy, we can decrease the voltage. But now let's see how we can incorporate a potentiometer in this circuit. So this is one way in which you can do it. So let's say this is R2 and the potentiometer is R1. Let's say R2 is a 1 kilo ohm resistor and R1 is, let's say, let's make it a 10 kilo ohm resistor. And let's use a 12 volt battery. So what we're going to do is we're going to calculate the range of the voltage across R2. So R1 can vary between 0K and 10K. So let's calculate the output voltage when R1 is set to 0K. So we know the output voltage is going to be the input voltage, which is 12, times R2 over R1 plus R2. So when R1 is 0K, you can just eliminate R1 out of the equation. It's going to be R2 over R2, which cancels to 1. So the output voltage will be 12. So let's say V out is equal to 12 volts. Now what about if R1 is set to its maximum value? In this case, R2 is still 1K, R1 is 10K. So it's going to be 12 times 1K divided by 11K. So the minimum voltage of this circuit will be 1.09 volts when R1 is adjusted to its maximum value. So using this potentiometer, we can adjust the voltage across R2 from approximately 1 volt to 12 volts. So that's another application of potentiometers. Now the way we connected this potentiometer was different than what we did before. This time, instead of just using 2 of the 3 pins, we used all 3. So I want to talk about when you see a circuit when you see a potentiometer connected that way. I want you to understand what's happening here. So we have our 3 points, point A, point B, and point C. And let's use a 100 kilo ohm potentiometer. Let me adjust this. So let's say point C is closer to point A, such that this is 25K and this is 75K. So the resistance between B and C will be 75K if B and C are not connected to each other. But what happens if we make a connection between B and C? Well, let's say we have a 10 kilo ohm resistor. That's going to be the resistance between point A and point B. But if we were to connect a wire between point A and point B, what's going to happen? Well, when electrons enter this circuit, they don't want to flow through the resistor. They're going to flow through this conductor because there's less resistance. And so the wire bypasses the resistor. The resistance between A and B is now 0 ohms due to the wire that's connected across the resistor. So once we connect B and C, the resistance of B and C is wiped out. So the resistance between A and B is no longer going to be 100 kilo ohms, but 75 kilo ohms out of that 100 kilo ohms will be wiped out. So it's only going to be 25K. So the electrons, they will flow through 25 kilo ohms of resistance. After that, they're not going to flow through the other 75K. They're going to go through this conductor to get to point B. So when you connect it this way, just understand that the resistance will be whatever the resistance is between point A and C. That's going to be the resistance between A and B. Now, I want to go back to the LED, the light emitting diode. As mentioned before, an LED converts electricity into light energy efficiently without generating much heat. But there's a device that works in the opposite direction, and that is a solar cell. A solar cell converts light energy, typically from the sun, into electricity. And so a solar cell is a power source, more specifically a DC power source. It kind of works like a battery in the presence of light, generating electricity that can be used to power your circuits. Now, we need to talk about DC sources and AC sources. DC stands for direct current. If we were to plot a graph between the voltage of a DC source and time, the voltage provided by a battery or a solar cell is relatively constant with respect to time. Now, of course, the battery is going to run out of energy, but if you're not consuming too much energy from the battery, the voltage will be relatively constant. The voltage can drop if you pull out too much current from the battery, so just keep that in mind. But in the ideal scenario, the voltage is, for the most part, constant. In an AC current, or let's say if you have an AC power source, the voltage varies with time. The voltage is not constant. It will fluctuate. It will go up, and then it will go down. So the voltage will vary between positive values and negative values. So a 10-volt AC source will vary between positive 10 and negative 10. Now let's talk about what that means in an actual circuit. So here we have a DC power source, a battery, and a resistor. In this circuit, current, that is conventional current, flows in only one direction. It flows from the positive terminal to the negative terminal. But keep in mind, electron flow is in the opposite direction. Now let's see what happens if we have an AC power source connected across a resistor. One source of an AC power source, well, at least you can find an AC power source in your home, that is in the wall outlets. In the US, typically the outlet power is 120 volts AC. But let's say we have a 12-volt AC power source. So what's going to happen is the current changes direction. At one instant of time, the current will be flowing in the clockwise direction. In another instant of time, the current can change direction and flow in the counterclockwise direction. So the current is constantly changing direction. It's flowing in one direction and then it flows in the other direction. Now, the number of times that the current changes in 1 second is known as the frequency. In the US, the frequency of a typical 120-volt AC outlet is 60 Hertz. So this means that the current flows in one direction and then reverses direction. That's one cycle. So it performs 60 cycles in 1 second. It travels in one direction, reverses, and it does that 60 times in a single second. So that's what the frequency of the AC power source tells you. How many times the current changes direction every second. So now you see the difference between a DC power source and an AC power source. So DC stands for direct current, AC stands for alternating current. Now you might be wondering, how can I convert a DC power source into an AC power source? Well, here are two ways you can do so. You could use a device known as an oscillator. An oscillator is a low power circuit that converts the DC power source from a battery into a sinusoidal wave or an AC output. Now with an oscillator, you can generate very high frequencies. You can get a frequency of 60 Hertz, 1 kilohertz, a megahertz, which is a million hertz, and so forth. Now for those of you who want to see how to build an oscillator, I have many videos on that topic. So if you go to the YouTube search box and type in oscillators organic chemistry tutor, you should see a bunch of them come up. And in those videos, I have the exact values of the components that you can use if you want to build an oscillator yourself. Now there's many different types of oscillators out there. You have the phase shift oscillator, you have the Hartley oscillator, the Colpitts Oscillator, the Esaki oscillator. There's a bunch of them. And basically, most of these oscillators will convert a DC signal into a sinusoidal AC signal or a sine wave. There are other oscillators where you can convert a DC input into, for instance, let's say a square wave. In this case, you would use the 555 timer, which is very useful for that. And once you have a square wave, you can convert that to a triangle wave using an RC circuit. You can even convert the square wave into a sine wave using an LC circuit. And there are other types of oscillators that may create like spike waves and just a whole bunch of different shapes. But the most common I've seen are the sine waves, the square wave, and the triangle wave. Now, an oscillator is not the only way you can convert a DC power source into an AC power source. In fact, when dealing with power electronics, you want to use a different device, something known as an inverter. An inverter is a circuit that takes high energy DC power sources and convert it to high energy AC power sources. So I'll give you an example in my case. When one time the power was out and I needed to do some work on my laptop, and after the battery in my laptop ran out, what I had to do was I had a 200-watt inverter. That may not be the exact power, but somewhere close to 200 watts. But I connected it to the 12-volt DC outlet in my car, and this inverter converted that energy to 120 volts AC, and I was able to connect my laptop to this inverter to charge up the battery and to get some work done on it. So this device could be useful when the power is out. Your car battery, or let's say if you turn on the car, it can be used as a generator so that when the power goes out, you can still power some electronics that don't use up too much energy. So that's another useful device to have around, especially if the power goes out. But now let's go back to low power electronics. That is batteries. There's something I do want to mention regarding batteries, and that is when you have multiple batteries, because you can use them to increase the voltage, decrease the voltage, or even change the current that can be dished out in a circuit. So let's say we have two batteries connected in this configuration. Let's use a 12-volt battery and a 3-volt battery. Now we're going to say that this point represents the ground potential. Now let's call this point A and point B. What is the potential at point B? So going from A to B, notice that this is a voltage rise. We're going from negative to positive, so the voltage is going to go up by 3. And going to or through the second battery, we're going from negative to positive, so that's a voltage rise. So thus, the potential at point B will be 15 volts. Now it's important to understand the difference between potential and voltage. So let's say this is point A and this is point B. Let's say the potential at point A is 12 volts. The potential at point B is 20. The voltage across this resistor is the potential difference of B and A. So the voltage is 8 volts. So make sure you understand the difference between voltage and potential. Voltage is the potential difference between 2 points. So going back to this example, by connecting the two batteries in this configuration, where the positive terminal of one battery is connected to the negative terminal of the other battery, you can increase the voltage of the two batteries. So the total voltage is now 15 volts. Now notice what happens if we reverse the connection of the 3-volt battery. So once again, let's call this our ground potential, which we're going to assign it a value of 0 volts. We could assign it any value, but 0 is a nice number. And let's put the sign of the terminals of each battery. Now going from point A to point B through the first battery, that is the 3-volt battery, notice that we're going from positive to negative. So that is not a voltage rise, that's a voltage drop. So that's a drop of 3 volts. Now going from this the negative terminal of the second battery to the positive terminal of the second battery, that is a voltage rise. So thus the voltage across A and B will be 9 volts. So based on the way we connect the two batteries, we can increase the voltage or we can decrease the voltage. So that's what happens when you connect two batteries in series with each other. You can make the voltage go up or you can make it go down. But what happens if we connect two batteries in parallel to each other? Well, let's say that this battery can dish out a current of 10 amps. If we connect two such batteries in parallel to each other, where each of them can release 10 amps of current, then the total current released by the two batteries will be twice the value, 20 amps. So if we want to increase the amount of current that we can obtain from a power source, you want to connect the power sources in parallel. If you want to increase the voltage of multiple power sources, you want to connect them in series with the positive terminal of one power source to the negative terminal of the other DC power source. Now the next thing I want to talk about is the light-dependent resistor. This is also known as a photoresistor. As the name suggests, the resistance of this element depends on the amount of light shining upon it. As the light intensity increases, the resistance decreases. And so there's an inverse relationship between these two factors. And there's a lot of applications with this type of a circuit element. For one example, you can create a night activated switch. This is video on YouTube if you want to search it out that I've created. It's called Night Activated LDR Sensor Circuit. And what it does is if you turn off the light, the circuit causes the LED to be activated. The light emitting diode begins to shine when it's dark. And this is very useful because let's say if you have one of these night lights in your home, when you turn off the light, these lights will activate. So your house is not very dark where you can't see where you're going. It's very useful to have these in your home, especially if you're coming home at night and you can't see where the light switch is. Having these night lights active at nighttime where it's not so bright but bright enough so you can see where you're going, they're very useful. And so this circuit element, the light dependent resistor, is very useful for creating night activated LED circuits. So check out that video when you get a chance. I'm also going to post a link to that video in the description section below if you want to look for it there. Now the next type of resistor that I want to talk about is the thermistor. The thermistor is a temperature dependent resistor. Now there's two types of thermistors. There is the PTC thermistor and there is the NTC thermistor. PTC, that's the positive temperature coefficient thermistor. NTC, that's the negative temperature coefficient thermistor. With the NTC, as the temperature goes up, the resistance goes down. And so there's an inverse relationship. With the PTC, as the temperature goes up, the resistance goes up. NTC thermistors are typically used as temperature sensors, whereas the PTC thermistors, they're typically used for resettable fuses. Now you might be wondering, what is a fuse? Perhaps you've seen this in your car, but a fuse is a device that is designed to protect a circuit in the event of a high energy surge. So let's say if we have a 10 amp fuse. If the current is 10 amps or less, that's good. If the current were to go above 10 amps, the fuse is designed to work in such a way that this wire filament would snap if the current exceeds 10 amps. And this protects the circuit from being damaged by a high current surge. And so the fuse is designed to break the circuit or open the circuit in the event of a high current surge. But the problem with that is once this wire snaps, the circuit is not going to work anymore. You have to replace the fuse. And so resettable fuses is very useful in this case because you don't have to replace it. So let's talk about the resettable fuse. So here we have a positive temperature coefficient thermistor, and we have a current flowing through it. When the voltage across this resistor goes up, the current goes up. And for a while, everything is going to be okay, but if the current keeps going up, eventually the temperature is going to go up. And when the temperature goes up, that's going to affect the resistance. The resistance is going to go up. And we know that when the resistance goes up, the current goes down. And so the PTC thermistor is designed to prevent too much current flowing in the resistor. Because when the temperature goes up and when the current goes up and the temperature goes up, the resistance is going to go up to bring back the current down. And so it prevents the current from getting too high. And thus it works as a resettable fuse. As the current goes back down, eventually the temperature will cool down. And so a system of equilibrium will be achieved. If we were to graph the situation, let's say if we put voltage on the x-axis and current on the y-axis, initially we would get something like this. So when the voltage is low, as we increase the voltage, the current is going to increase steadily. The slope is going to be relatively constant, while the temperature is constant. As we continue to increase the voltage, eventually the current is going to get to a point where it's high enough to cause an increase in temperature. And when the temperature goes up, the resistance is going to go up, bringing down the current. So the current is not going to increase at the same rate. So eventually it's going to taper off. It's going to increase at a decreasing rate until it reaches a constant level. And so at this point, that's where the PTC thermistor acts as the resettable fuse, where as you increase the voltage above a certain point, the current is going to be relatively constant. So this device is very useful for maintaining the current when the voltage gets too high. Now let's talk about some applications of the NTC thermistor. So you can use this as a temperature sensor, and here's one example of that. So we're going to connect the NTC thermistor to an LED. Let's use a 9-volt battery. So what's going to happen when the environment is hot? When the temperature increases, the resistance of the NTC device is going to go down. And when the resistance goes down at constant voltage, the current is going to go up. If the current in the circuit goes up, the brightness of the LED increases. Now let's see what happens in a cold temperature environment. As the temperature decreases, the resistance goes up. If the resistance goes up, the current goes down. If the current flowing through an LED decreases, the brightness decreases. So in this particular circuit, notice that there's a direct relationship between the temperature of the environment and the brightness of the LED. When the temperature goes up, the LED gets brighter. When the temperature goes down, the brightness cools down. So the brightness of the LED in this circuit indicates how hot or how cold the environment is. So in this way, you could use the NTC thermistor as a temperature sensor, where the brightness of the LED is a reflection of the temperature of the environment. Now, the relationship between temperature and resistance is not a linear relationship. In fact, as the temperature goes up, the resistance decreases in such a fashion. Now, there's an equation that describes the relationship between temperature and resistance for these types of devices. I do have a video on thermistors, so you can do a YouTube search on that and you'll find it. But now let's move on to capacitors. Capacitors are devices that store electrical energy by means of an electric field. Another device that can store energy is inductors, but inductors can do so through the magnetic field that they create. So here's an example of the storage capacity of a capacitor. So here we have an LED, and we're going to use a 10 kilo ohm resistor. Let's use a 12 volt battery. And we're going to use a capacitor that can store a relatively large amount of energy. We're going to use a 16 volt 4700 microfarad capacitor. So when dealing with electrolytic capacitors, these are polarized capacitors. This is the positive plate, this is the negative plate. Two important things you need to look at is the maximum voltage rating of a capacitor and the capacitance. The capacitance tells you how much energy the capacitor can store, or rather, more specifically, its ability to store charge. I won't go into too much math, but the potential energy stored by a capacitor is 1/2 CV squared, where C is the capacitance, V is the voltage. So as you increase the capacitance of a capacitor, it can store more energy. And if you can increase the voltage, it will also store more energy as well. Right now the switch is open. So let's talk about what's going to happen if we close the switch. Initially, if we close the switch, current from the battery will be used to charge the capacitor. And some of the current will also activate the LED. So the LED is going to turn on. Now once the capacitor is charged and we open the switch again, no current will be able to flow from the battery. However, the capacitor will use its stored energy to keep the LED going. So the LED will remain on as the capacitor discharges its energy through the LED. So in this way, it shows the capacitor's ability to store electrical charge. Now eventually, the energy is going to run out, so the LED is going to get dimmer and dimmer until it turns off. Now let's talk about the different ways in which we can connect capacitors. So when we talked about resistors, we can connect them in series or in parallel. We can do the same with capacitors. So these three capacitors are connected parallel to each other, which means that they have the same voltage across it. So anytime you have multiple elements connected in parallel to each other, the voltage across each of those elements will be the same. The total capacitance of three capacitors parallel to each other is the sum of those capacitors. Now we can also connect capacitors in series with each other. If you do so, you could use this equation to calculate the total capacitance. It's 1 over C1 plus 1 over C2 plus 1 over C3. And this is raised to the minus 1 power. So when you connect capacitors in parallel, the total capacitance increases. When you connect them in series, the total capacitance decreases. Now you can also use capacitors to increase the voltage. For instance, let's say you have a 12 volt battery and you have three capacitors connected parallel to the 12 volt battery. Each of these three capacitors will be charged to a voltage of 12 volts. So after some time has elapsed, the voltage of the capacitor will increase from 0 to 12 volts. Now once these capacitors are fully charged, you can disconnect them and then reconnect them in series. If you reconnect them in series, the total voltage is going to be the sum of the voltages across the three capacitors. So it's now going to be 36 volts. So that's one way in which you can use capacitors to increase the voltage. Now you can also use capacitors to increase the current. For instance, so let's say you have a battery connected to a supercapacitor. A typical electrolytic capacitor will have a capacitance of 1 microfarad to 4,700 microfarads. Actually, it could range from 0.1 to 4,700 microfarads for electrolytic capacitors. For supercapacitors, you're talking about capacitance of 10 farads, 100 farads, 1,000 farads. So let's say we have a 100 farad supercapacitor. The downside is the voltage is typically low. The maximum voltage for a supercapacitor is around 2.7 volts. And so we don't want to exceed that. So let's use a 1.5 volt battery. Now, if you were to connect a 1.5 volt battery to a short circuit, the current that can be measured from this battery, let's say like a typical AA alkaline battery, might be anywhere from 5 to 10 amps. Now, the reason why the current is limited is not because of the conductance of the wire, but because of the internal resistance of the battery. However, a supercapacitor's internal resistance is very low, which means it can discharge a lot of current. So let's say that this battery charges up the capacitor at a current of 1 amp for 100 seconds. Let's say this is an average current, because as the voltage of the capacitor increases, the current flowing in the circuit will decrease. So let's say the average current is 1 amp for 100 seconds, just to keep the math simple. Once this capacitor is charged to 1.5 volts, or the voltage of the battery, let's disconnect it and let's create a short circuit. If we were to measure the current will be very high for a short period of time. So here it's being charged for an average current of 1 amp for 100 seconds. Here you might get an average current of 100 amps for 1 second. So in this example, it took a long time to charge this capacitor. So we got a small amount of current being applied to this capacitor over a long time period. But when the capacitor discharges its energy, it can discharge a very large current for a short period of time. Energy is not created in this process, it's simply stored. But notice how the capacitor can increase the current by decreasing the time in which that current is active. So capacitors can be used to discharge very large amounts of current, which can be useful in certain applications. Now, notice that in this example, the charge is conserved. The charge, represented by the symbol Q, is equal to the current multiplied by the time. So the charge that was delivered to the capacitor in this example is 1 amp times 100 seconds, which is 100 coulombs. And the charge that was delivered by the capacitor is 100 amps times 1 second, which is still 100 coulombs. So energy is not created or destroyed here. It's simply being discharged at different rates, so to speak. Now, if you were to actually measure this, the actual numbers will vary, but the principle behind it is still the same. When the capacitor is charging, it's going to receive a small amount of current over a longer period of time, but when it discharges, it can release a large current over a shorter period of time. And that's the principle I want to help you to understand here. Now, the amount of current that the capacitor can discharge over a short period of time depends on the conductance of the wire. A very thin wire has a large amount of resistance and a small amount of conductance. So if you were to use a thin wire, the current flowing through it will be less. If you were to use a thicker wire with a greater cross-sectional area, the resistance of such a wire is much lower, and so they can handle more current. So the bigger the wire in terms of its thickness, the greater the current that can flow from the capacitor. So the amount of current that will be discharged from the capacitor in a short circuit depends on the resistance or the conductance of the conductor. Resistance and conductance, they're inversely related. The conductance of a conductor is just the inverse of the resistance. So let's say if you have a wire with a resistance of 0.1 ohms, then the conductance is 10, and the unit for conductance is Siemens. Let's say if you have a bigger wire with a resistance of 0.01 ohms. The conductance is 100 Siemens. Now I'd like to discuss some similarities and differences between two important components, capacitors and inductors. There's a lot of things that you can create with these two devices, but what I want you to know is that capacitors, they can store electrical energy by means of an electric field. Inductors can store electrical energy by means of a magnetic field. Capacitors are useful to maintain the voltage across an element. Inductors can be useful to maintain the current flowing through an element. As mentioned before, the energy stored by a capacitor is 1/2 CV squared. So the voltage across a capacitor is very important in determining the energy stored in the capacitor. In the case of an inductor, the potential energy stored in an inductor depends on the current flowing through it. The more current that flows through an inductor, the more energy it stores. Now there's two types of circuits that you may want to research: the boost converter and the buck converter. In the boost converter circuit, an inductor is used to increase the voltage. In a buck converter circuit, the inductor is a very important element that can be used to decrease the voltage by increasing the current. We saw how using a potentiometer in a voltage divider network, we can decrease the voltage. But we're decreasing the voltage through the dissipation of energy. And so using a potentiometer to reduce the voltage is not efficient. We're losing energy. But when you use a buck converter to reduce the voltage, it's more efficient because as you reduce the voltage, the current goes up. So that's one advantage of the buck converter circuit over the potentiometer voltage divider network. With the boost converter, you can increase the voltage of a DC power source greatly. You can turn a 9-volt battery into a 100-volt power source. So I'm going to talk briefly about how that circuit works. So we need a battery, an inductor, and we need a switch, a diode, a capacitor, and a load resistor. Let's use a 12-volt battery. As current flows through the inductor is going to absorb energy. And so there's going to be a voltage drop. Let's say that voltage drop is 8 volts. And let's say we're using a germanium diode, which has a voltage drop of 0.3 volts. At this instant of time, the voltage across the load resistor will be 12 minus 8 minus 0.3. So it's going to be 3.7 volts. And so the capacitor will be charged to 3.7 volts. Now, right now, as the current flowing through the inductor increases, the magnetic field in the inductor will begin to expand. Anytime there's a current flowing through an inductor, there is a magnetic field. The strength of the magnetic field depends on the value of the current. So as the current goes up, the magnetic field gets stronger and it expands. And so right now, the inductor is storing energy. It's absorbing energy from the circuit. Now, when the switch is closed, that is S1, notice what's going to happen. When we close the switch, current is going to continue to flow through the inductor, and it's going to go through the switch. In this case, we're going to get a large amount of current. So this current is going to increase. The magnetic field will expand even more. So right now, the inductor is storing a lot of energy. Now, when the switch is open, the current flowing through the inductor is going to decrease. It's not going to be as high as it was when the switch was closed. Now, as the current in the inductor decreases, the magnetic field, which was very large when the current was high, that magnetic field will collapse. And as it collapses, it's going to induce a voltage across the inductor. And the polarity is going to be opposite to what it was before. Now that the magnetic field collapses, what's happening is the stored energy in the magnetic field is now being converted into electric energy. The inductor is giving back the energy that is stored in the first part of the circuit. And now the voltage will be relatively high. It can be a lot higher than 8 volts. It can be 30 volts. It really depends on how fast the current is changing. So now the voltage across the capacitor will be 12 plus 30, that's 42, minus 0.3, so that's 41.7. So the collapse in magnetic field inside an inductor can generate very high voltages. And in the boost converter circuit, which is what we're dealing with now, we can generate super high voltages using an inductor. And then we can store that voltage using a capacitor. So now you understand how inductors can be used to generate very high voltages. It's due to the collapse in the magnetic field that occurs when the current decreases. But now I did mention that capacitors can be used to maintain voltage and inductors can be used to maintain the current. So let's talk about how inductors can maintain the current. So let's say we have a current flowing through an inductor. When the current increases, the magnetic field will expand. The inductor is absorbing energy from the circuit. And so the voltage across the inductor will be as follows. And that voltage impedes the current flowing through it. And so when the current increases, the inductor acts in such a way to decrease the current because it's absorbing energy from the circuit. In that way, it helps to maintain a relatively constant amount of current. If you were to connect a battery across a resistor and you were to apply current and time, the current will increase almost instantly from 0 to its maximum value. But if you were to connect a battery and an inductor in series with a resistor, the current won't increase drastically. It will increase gradually. So in the presence of an inductor, it can't increase immediately. So in that way, an inductor helps maintain a relatively constant amount of current. Now let's see what happens when the current flowing in an inductor decreases. So that means initially, the magnetic field is very high. When the current goes down, the magnetic field will collapse. And when it collapses, the polarity across the inductor changes. And so now the inductor becomes a current source. It helps to support the falling current. So when the current goes up, the inductor tries to decrease the current. When the current goes down, it tries to increase the current. So the inductor is very useful for maintaining a relatively steady amount of current flowing through a device. So that's basically it for this video. I'm going to stop it here. Hopefully you found it to be helpful and educational, but thanks for watching.